In section 3 of chapter 6, we're going to be analyzing rational functions using what is called interval notation. Now, technically, I could have taught you this lesson earlier, specifically when we were doing that chapter on graphing. However, in those chapters, all of them would have been exactly the same. You can always dictate the domain of a function using interval notation for any function. It's not until now that we've gotten to rational functions that the domain starts to manipulate and change in a way that showcases some of the unique features of this type of notation. So, without further ado, I first want to discuss what I mean when I say the word domain, and then show you what I mean with interval notation. Domain is a simple thing. It is asking what numbers can you plug into the function. That's all the domain is. It's a list of the numbers you can substitute into the function. That is usually all real numbers. Like a quadratic, you can plug in any number you want. A linear function, absolute value function, exponential, you can plug in whatever number you want. Positive, negative, decimals, fractions, you can plug in anything you want. It is not until you get to the two subcategories of functions where things start to get a little different. Namely, square roots and rational functions. Because if you remember I said there are two things in mathematics you cannot do. You cannot square root negatives, and you cannot divide by 0. Those are the two things in algebra you are not allowed to do. Now we're going to remedy one of those later, and then the other one you'll remedy in calculus. But for problem number 1, I have the square root of x. There is a domain restriction on this. The domain restriction is x has to be greater than or equal to 0. It has to be a positive number. That's what that means using inequalities. Problem number 2, I have the square root of 2x minus 3. If you wanted to, you could set that equal to 0 and solve, but you'd ultimately find that x has to be greater than or equal to 3 over 2. That is the domain restriction for problem number 2. Now, problems 1 and 2, their domain restrictions are sets of numbers. They say x has to be this large set of numbers. That is different than problems 3 and 4, which are rational functions. Their limitation is x can be any number you want except for this selected list of a few numbers. So for problem number 1, x can be any number you want, positive, negative, fraction, decimal. But x cannot be 0. That is the limitation. So it is distinctly different than like problem number 1. 1, there's a bunch of numbers x can't be equal. Number 3, there's only 1. And problem number 4, same thing. X would not be allowed to be equal to negative 2 over 3. All of these are domains written with inequalities. You've probably seen this stuff before, at least problems 1 and 2. I'm going to show you how to write those exact same statements in a different format. I will forewarn you, the formatting I'm about to show you, there's going to be some new symbols. It is one of my pet peeves in algebra because the symbols that were adopted for this notation are also used in other areas of mathematics. And to be honest, there is a little bit of confusion between them when you see it on problems. It is important that you recognize them and these symbols as having two meanings. Because if you're not aware of that, they will sneak up on you and you will think it means one thing when in fact it means the other. So, I need another way for problem number 1 of saying x is greater than or equal to 0. How about instead of writing it as an inequality, I write it as a range of numbers. I say, okay, x has to be between 0 and go all the way to infinity. However, 0 is included as part of that answer. So the symbol we use is a bracket. Brackets are inclusive. They mean I include 0 as part of my list of solutions. And then it goes all the way to infinity. Infinity is not a number, so I can't include in my list of numbers infinity. So I have to have a symbol that means not infinity. The symbol we use is a parentheses. This is interval notation. These two things are exactly the same. They're just using different notations. So again, a bracket means we're including the value. A parentheses means we are not. Brackets are inclusive. Parentheses are exclusive. So problem number 2, same thing. I'm going to go from 3 over 2 all the way to infinity. I'm going to include 3 over 2. I am not going to include infinity. Starts getting a little more spicy with problems like number 3. Number 3, I want every single number except for 0. So in fact, I'm going to start at negative infinity. I'm going to go all the way to 0. I cannot include negative infinity, so I'm going to put a parentheses. 0 is not a number I include, so I'm going to put another parentheses. And then I'm going to leave a little space. I'm going to show you another symbol. It's going to pick back up again on the other side of 0 and go all the way to infinity, but also not include infinity. Now, as it's written right now, each of those is an individual interval. I need a way of saying I want both intervals at once. The symbol we use is called a union symbol. It looks like a capital U. This is the interval notation for all real numbers except for 0. And then lastly, problem number 4, same thing. We're going to go from negative infinity all the way to negative 2 over 3. We can't include either of them, and it'll be the union of that interval with the interval from negative 2 over 3 all the way to infinity. And that is the interval notation for x cannot be equal to negative 2 over 3. The last thing I want to do is I want to go back to rational expressions, rational equations, and write the domain restrictions using interval notation without actually showing the inequality notation. I'm going to go straight from the problem, straight to interval notation. So problem number 1, I recognize x cannot be equal to negative 1. Therefore, the interval notation is negative infinity all the way to negative 1, union negative 1 to infinity. Problem number 2. Now, this is something that students get tripped up on. They look at this and they say, Mr. Silva, these x's eliminate. Does that mean it's not part of the interval notation? We do interval notation before we do any kind of simplification. We just care about the discontinuities. All I care about is that x cannot be equal to 0 or negative 3. I don't care which of the two categories they fall into. I don't care if they're removable or non-removable. They both, for interval notation, mean the same thing. It's going to go negative infinity to negative 3, union negative 3 to 0, union 0 to infinity. For every inequality, for every single one of these discontinuities, you need a new union symbol. And then lastly, problem number 3. This is the most annoying one, because problems 1 and 2 were already factored. Problem 3 is not. Now luckily, because all we care about are the discontinuities, not what type they are, we don't need to factor the numerator, because we don't care if stuff cancels on top and bottom. All I want to do is factor the denominator. Factor out a negative 5x, and that will give me a x squared plus, nope, not plus, minus 4x plus 3, which then would factor into x minus 3 times x minus 1, which means x will not be equal to 0, 3, or 1. Here's a challenge for y'all. I want to do the next step wrong. I want you trying to answer internally. Don't ruin it for everyone else. How did I do the next step wrong? Everything I've done right now is correct. Here's my interval. Negative infinity to 0, union 0 to 3, union 3 to 1, union 1 to infinity. That's wrong. Take a moment to kind of ask yourself, why is it wrong? So this interval is wrong because these were not in the proper order if you want to just copy and paste it. They need to be from smallest to greatest. So it should read negative infinity to 0, union 0 to 1, union 1 to 3, union 3 to infinity. And then lastly, I felt like throwing on a little bit of a trick problem for number 4. We're trying to find all the numbers that you can plug into x. The limitations for algebra: you can't square root negatives, you can't divide by 0. That's why we've been analyzing rational functions, and previously we did a little bit of analyzing square roots. Problem number 4 is a quadratic. I'm not going to square root anywhere in the problem. I'm not dividing by x anywhere. That's just a straightforward problem. Its domain is negative infinity to infinity. I can plug in any number I want. Or you could say all real numbers, which is a capital R with an extra line through it. That's the symbol for all real numbers, just as a little aside.